Hi everyone and welcome to the Hasty YouTube channel. My name is Vlad and I work as a content manager at Hasty AI. In this video, I wanted to tell you about a fascinating project we did with the power of Hasty features. In short, we cleansed a popular object detection benchmark dataset, PASCAL VOC 2012, trained two models, one on the original labels and the other on the improved ones, and got a significant mean average precision metric value improvement for the second model. Without further ado, let's get started. As you might know, there is a data-centric AI development approach suggesting that you can upgrade your model's performance by improving the quality of your data. In short, better data results in better models. That is precisely what we tried to achieve throughout our project. We took an old dataset with some annotation issues, fixed them, and then checked whether it positively impacted the model's performance. And yes, it did. We spent 80 person-hours cleansing Pascal. On the way, we added about 3,000 new labels to the Pascal's training set and adjusted almost 200 existing ones. The result, though, was more than worth it. As you can see on the graph, the orange model performed way better than the blue one. So, to be precise with the numbers, the model trained on the updated Pascal worked by 13% better than the model trained on the original Pascal. Let me show you how we achieved it. As a dataset, we chose PASCAL VOC 2012, which is a well-known academic dataset used for benchmarking models for vision AI tasks such as object detection and semantic segmentation. Even though Pascal is over a decade old, it's still frequently used. It was used in 160 papers in 4 recent years. To clarify, we didn't do the quality control process manually. We used one of the Hasty features, AI consensus scoring, which looks for the potential mistakes in your labels using a variety of AI algorithms. In this screenshot, you can see the results of an AI CS run where the tool has found some labels that were missed in the original annotations. AI consensus scoring checked Pascal for the annotations with the wrong class, bounding boxes of the wrong shape, different artifacts, extra labels, and missing annotations. Our goal was to review the potential errors found by AICS and resolve them while trying to be more accurate than the original annotators. In simple words, it means that we tried to fix all possible issues on every image where our AICS predicted at least one potential error. As you can see on the screenshot, AICS has found 2 missing person labels, but there are still 3 or 4 more annotations that should have been on this image. So we fixed that by annotating all of them. Also, we didn't go deep into the background and didn't aim to annotate every object possible. If the annotation missed an object and was in the foreground and or visible by a human eye without zoom, we labeled it. On an image on the right, we annotated only the horse, not the people in the background. Additionally, we tried to make our bounding boxes pixel perfect. And we annotated partials, the unlabeled parts of the dataset's class object, because, well, the original dataset features them. In these screenshots, you can clearly see that the original annotators still labeled an object, even if it wasn't 100% visible. To be honest, when it came to fixing the annotations, it wasn't that hard of a task. With the potential errors highlighted, we could just simply go through the suggestions and occasionally do something manually. Such a format for quality control streamlined the process as we didn't have to search for the errors manually. The Hasty UI allows you to directly feature potential errors in the annotation environment. So all we had to do is to filter the images with unresolved errors, toggle on the Show Errors on Canvas flag, and click on each exclamation mark on every image to see the suggestion and either accept or reject it. Let me show you a quick resolving time lapse for you to get the feeling of the speed of the quality control process with AI consensus scoring. When everything was ready, it was time to train some custom models. We decided to train two models, one on the training set of the initial Pascal and the other on the training set of the improved Pascal. As a validation set for both models, we used the validation set of the initial Pascal. You must be wondering what the exact parameters we use for our custom models are. Well, here they are. We went through a set of experiments trying to identify the best hyperparameters for our case. We started with the faster RCNN academic paper that features using this architecture on Pascal. Then we just tried to achieve the best result possible by adding the deeper backbone, the learning rate scheduler, and a variety of augmentations. The parameters presented on the slide are the ones we stopped on. To train the models, we used Model Playground, the no-code model building feature offered by Hasty. To learn more about the feature, please use the QR code to get to the products page or click on the corresponding link down below. Let's check how it looked from the Hasty UI perspective. To use Model Playground, you simply choose the parameters from the available options. So all you need to do to train your own neural network is click on several buttons and wait until the model is ready. As you can see, here are all the parameters featured on the slide. So for example, the architecture, the backbone, the initial weights, then there are the augmentations, all of them. Then, of course, there is the solver and the scheduler. And last but not least, the metric itself. To give you more detailed results, we spent roughly 80 person-hours reviewing all the suggestions and cleaning up the dataset. It is a fantastic result. Many R&D and data science teams that use the conventional approach of manual quality control would die for an opportunity to review 17,000 images in that time frame. With the help of AICS, we found out that annotators use the sofa and chair classes interchangeably. As you can see on the right, there are two sofas and two armchairs on an image. Still, in the original annotations, one of the two armchairs is labeled as sofa, whereas the other is annotated as a chair. Seems weird and worth fixing, and we did it. The armchair is a chair and the sofa is a sofa. We fixed these issues by relabeling more than 500 labels across the dataset. When analyzing the AICS runs, we found out that Pascal's most prominent issue is not misclassified annotations, weird bounding boxes, or extra labels. The most significant problem it has is the absence of many potential annotations. It is hard to estimate the exact number, but we feel like there are thousands of unlabeled objects that should have been labeled. So, with the help of AICS, we found and labeled more than 6,000 missing annotations. Speaking about the models, we got the results we hoped for. The proof that data-centric AI development is a thing. Throughout the project, we didn't try to beat any state-of-the-art or get results better than the previous researchers. We wanted to show the world that sometimes spent improving the data benefits the model's performance. And we hope that our case, which gave us the 13% mean average precision increase by adding 3,000 missing labels to the training set, was convincing enough and encourages you to find and fix some issues in your own data. When we shared our results with the world, we got a lot of attention from the people fascinated by the computer vision field. We are extremely thankful for each and every comment, upvote, repost, and discussion. Thank you very much. Our work gets you talking about the field, and that's why we keep pushing further and further. Still, we got some criticism. The main point was that the validation curves were of a weird shape. It is a fair point, as you can clearly see a sudden jump on the orange validation curve. The community suggested that the improvements occurred because of the learning rate decrease, not the improved data. We started investigating and found out that for some reason the scheduler didn't work for the blue model, but worked for the orange one. Still, when building the models, we tried to achieve the best possible metric value to mimic a real-life development process in a sense rather than a lab research. That's why we used the scheduler. You would have used it as well. The outcome, though, is quite interesting. Let's see what we can do about it. Such criticism is awesome because it gives us the motivation to work further. That's why right now we are working in 3 different directions that will give us a better view of the data-centric AI development approach. First, we are planning to train models without a scheduler or with a scheduler that doesn't have randomness in it. Second, we want to find and label even more missing annotations in PASCAL VOC 2012 and continue experimenting. And third, there is a thought to train models with some other initial weights. For example, the ImageNet ones. Seems like there is a lot for us to do. Subscribe to the channel and stay tuned to get the update first. Also, if you want to learn more about the project's workflow, please check out the initial post via a QR code or the link down below. Every single step in this project was done using Hasty. At Hasty, we are experts in building vision AI in an economically viable way. With our unique methodology enabled by our platform, we help many companies to deploy vision AI solutions in weeks, stay on budget, and move the needle for their business. So if you are looking for a way to ease your data annotation pain, or if you want to replicate such fascinating results as you've seen in this post, please visit our website and book a demo.